Okay, so hi, welcome to this next video in linear programming. This video is on the topic of convexity of polyhedra. So in the previous video, we were discussing how a polyhedron, by definition, is the feasible region of a linear program. And then we rewrote the format of a linear program so that instead of being in standard equality form, we wrote it as a bunch of less than or equal to constraints. So that's a linear program can be rewritten so that it's exclusively less than or equal to constraints. And when we did that, we were able to realize that a polyhedron is the intersection of half spaces, a finite number of half spaces. So we saw, for example, this purple shape here was the set of points that were feasible for that example linear program we had in the previous video. And if you just take a look at one specific constraint, so by when I say constraint, that is corresponding to an individual less than or equal to constraint, and then visually what that looks like is a line here, and that's geometrically speaking. And so when you look at that single constraint there, what you get is that the constraint, well, you have a line and then it splits space into two halves. There's the good half of space and the bad half of space. So the bad half is the set of points that don't satisfy the constraint, and the good half is the set of points that do. And remember, by constraint, it's a less than or equal to constraint now, because everything is less than or equal to constraints. We've written it like that. And by the way, this boundary line that splits the space into two halves, it's not so much a line, it's more of a high-dimensional object, but when it's in two dimensions, it does just kind of look like a line. But in general, it's a flat thing, it's a hyperplane. So that's a term that comes from linear algebra. It's a high-dimensional flat object. And so we could realize this polyhedron as the intersection of all the good half spaces. So the half space that satisfies that particular constraint, corresponding to this line here, everything less than or equal to, and then the same thing for this constraint and those other constraints, and just you look at the intersection of all those half spaces, and what you get is exactly this purple set here. And so the thing that we're going to show is that there's a geometric feature to these shapes, well, beyond the fact that it's a connected shape here, but they're so-called convex. So these polyhedra, in addition to being the feasible region of a linear program and being the intersection of a finite number of half spaces, they're also convex. We'll define convexity formally later, but first let's just get a formal definition for half space and hyperplane. So half space, when we say we're splitting space into two halves, the half space that we're concerned with, the good one, is it's the set of points x and Rn such that alpha transpose x less than or equal to beta. So alpha and beta are given data. So this is a single linear inequality here. And so you imagine that you have a linear program and it consists of many less than or equal to inequalities. And so we're just looking at a single individual one of those. And that would be this constraint here, alpha transpose x less than or equal to beta. And so the points that satisfy that, those are the points in this good half space. And then a hyperplane, that's the set of points that where alpha transpose x equals beta. So it still satisfies less than or equal to, but it satisfies it tight, exactly with equality. And so that would correspond to this line, because when you're strictly less, you're on the left-hand side here of the half space, and as you approach, you're getting larger and larger values for alpha transpose x. So I'm changing x, that's corresponding to moving in space, and then at some point you hit exactly this value of beta, and if you were to go any further, you'd be on the bad half of space, because that corresponds to being strictly larger than beta, and so that would violate the inequality. So, but when you're exactly equal to, that's this hyperplane. Okay, so that's what a half space and a hyperplane are, and we're going to use those constructs to show that polyhedra are convex. So that's our goal in this video. Our goal will be to show that polyhedra are so-called convex. So in other words, there's no dents. That's intuitively what you're imagining by convexity. So we'll give a formal definition of convexity, but first let's just kind of see intuitively what we're trying to capture by the idea of convexity. So these green shapes are convex, and these blue shapes are not. And so what makes something not convex is that there's a dent, So take a look at this blue shape here. There's a dent here, and so that's going to make it not convex. And so we can formalize that a bit more by considering taking 2 points within the shape. So I start at these 2 endpoints here, but then when I connect them via this the line segment that connects these 2 points, that line segment won't be entirely contained within this shape here, and that's because we have this dent, and so we can leave and then re-enter the shape, and since we leave and it's not entirely contained, that's what makes it not convex. Same thing here. You have to kind of be a bit more flexible with what your notion of a dent is, but still, what we have is 2 points. They're both in the shape, but when you connect them by the line segment that connects those 2 points, that segment is not entirely contained in the shape. And so if there exists 2 such points like this, that when you connect them by the line segment, even though the points are in the shape, the line segment is not entirely contained in the shape, then that is not convex. So that's in contrast to these 2 green shapes. This is convex because, visually you can just verify. No matter what you do, no matter which points you take, for every pair of points inside this object here, the line segment that connects them is also contained in this object. And similarly, this, it's not just for 2-dimensional things, it's for arbitrary dimension. So here's a 3-dimensional thing, or it's supposed to be at least, and this is a tetrahedron, and if I take any 2 points in the tetrahedron, doesn't matter where, I connect them by the line segment that connects those 2 points, then the tetrahedron will contain that entire line segment, no matter which points I take. So that's the idea of convexity. But of course, this is supposed to be for any dimension, so in high dimensions, we need a formal notion of what a line segment is, and then we can give a formal definition of convexity as well. So this comment over here is just addressing what we already said. In a brief way of saying things, non-convex regions don't contain all their line segments, whereas these do, convex ones do. So let's formalize the notion of line segment for high dimensions, and then we can define convexity in terms of line segments. Formally, if I take 2 points, x and y in Rn, then the line segment between x and y is this set here. It's lambda x plus 1 minus lambda y, where lambda is a parameter that ranges in between 0 and 1, and it includes both 0 and 1. You can see, for instance, that when lambda equals 0, when you plug that in, this first part vanishes, and you're just left with 1 y, so just y. And similarly, if you plug in y, lambda equals 1, then the latter part goes away, and you're just left with x. So you can get x and y when you plug in the boundary values of 0 and 1 for lambda. And then this is linear in x and y, and so I get the line segment connecting x and y. Lambda in between 0 and 1. You can verify that agrees with your intuitive notion of what a line segment is when you're in 2-dimensional space. Okay, but anyway, so that's by definition a line segment for high-dimensional points, or arbitrary dimension, really. Doesn't matter whether it's high or low dimension. And anyway, so then a subset C in Rn is said to be convex if no matter which 2 points in the set C that I take, the line segment between x and y that connects them is itself entirely contained in C. So that's what we mean. So when we say a convex set contains its line segments. So I take any 2 points in the set, and then that entire line segment connecting the points also has to be in the set, regardless of which 2 points I started with. Okay, so here's some examples of convex sets. So the 2 green shapes above, those are both convex. And the other things that are convex, half-spaces and hyperplanes. So we'll see why those are convex in just a moment. And then finally, the other relevant convex set is if I start with convex sets and then I take their intersection. So intersections of convex sets is itself a convex set. And in fact, that intersection can be infinite. I can have an infinite number of convex sets that intersect, or a finite number, it doesn't matter. But whatever it is, intersection of convex sets is convex. You can see the opposite. If I take unions of convex sets, there's no reason at all that needs to be convex. It's immediate. You can easily find examples for that that are not convex, but intersections are. So we're going to prove these red asterisked ones. So the first one you can just visualize, verify visually. The third one is very, very similar to the second one, so there's really no need to do two separate proofs. So we'll just do 2 and 4. And it's just by definitions. Okay, so proof for why a half space. Why is a half space convex? So first of all, what a half space is, it's the set of points in Rn that satisfies this given linear inequality. So what I want to do to show that this is convex is I want to take 2 points, x bar and y bar, in the half space. And what I want to show is that the line segment is contained in the half space. So here's the line segment. It's lambda x bar plus 1 minus lambda y bar. And for every value of lambda that I plug in, lambda equals anywhere from 0 to 1, as I range over that interval for lambda, all those points that it generates, which is the entire line segment, each of those individual points needs to be in the half space. So that's what it would mean for the half space to be convex. Because x bar and y bar are arbitrary points. Because we need to show it for every pair of points, x bar and y bar. Okay, so let's just, we can quickly see that we're just going to take this point here. So just imagine that this is any particular point on the line segment. As I plug in a value for lambda, I'll get any particular point on the line segment between x bar and y bar. And so alpha transpose times that. What I want to show is that this is in the half space. So that would mean I need to show that alpha transpose x times this is less than or equal to beta. That it, in other words, it satisfies the linear constraint. So anyways, just straightforward math here. It's just alpha transpose times this. I just distribute the alpha transpose into the addition. So now it's the sum of these two terms. And then we already know that x bar and y bar started out in the half space. So that means that alpha transpose x bar and alpha transpose y bar are both less than or equal to beta because they satisfy the inequality by assumption of the fact that they're in the half space. And so these are both less than or equal to beta. And then each of lambda and 1 minus lambda, they're both non-negative because of the values that lambda can take on. It's between 0 and 1. So these are definitely non-negative. So I have a non-negative linear combination of two things that are individually less than or equal to beta. And so then this entire thing is less than or equal to lambda beta plus 1 minus lambda beta. The lambda and the 1 minus lambda persist to this next inequality. And I just replaced these things with their upper bounds of beta. And then you can see that the lambda beta and minus lambda beta cancel, and I'm just left with beta. And so I get that alpha transpose times this thing is less than or equal to beta. And so in other words, this is an arbitrary point on the line segment, and so then therefore the entire line segment is contained in the half space, and that makes the half space convex. So yeah, okay, so there you go. And almost identical reasoning applies for showing hyperplanes are also convex. I would just basically be replacing a less than or equal to with an equal to. But yeah, so half spaces and hyperplanes are convex sets. And then also, why are convex sets, intersections of convex sets also convex? So I start with Cj convex for all indices j and some capital J. Capital J is just some index set, so it could be infinite, maybe it's finite, we don't know, we don't really care either. But Cj's, they're all convex. And now I want to show that the intersection of all those Cj's together is also convex. So again, it just goes by definition. So I start with 2 points, x bar and y bar, in this intersection. And so I want to show that the line segment between x bar and y bar is also in this intersection completely. And so anyways, if these 2 points are in the intersection of all these convex sets, then that means that they're in each of the individual convex sets, Cj, for every j and j. That's what it means to be in the intersection. And since each of these Cj's are individually all convex, that must mean that the line segment between x bar and y bar is contained in Cj for all j and j. But then that means that the line segment between x bar and y bar is contained in the intersection because it's in each of the individual CJs, and so therefore the line segment is contained in the overall intersection of the CJs. And since x bar and y bar are arbitrary, then that's for every pair of points, x bar and y bar, then the line segment between them is contained in this intersection of convex sets, which makes it itself convex. Okay, and so that those points that we just made allow us to draw the important conclusion that we wanted to draw this video, which is this boxed thing here, that polyhedra are convex. So there's lots of things that are convex, and they don't need to be polyhedra. There's many, many non-polyhedra things that are convex. For instance, you know, that top left green shape that we gave with the curve involved, you know, that's not a polyhedra, but it's still convex. But anyway, all we're concerned with right now are polyhedra, because they are the feasible regions of linear programs, and we're concerned with linear programs, and they are all convex. So that's the nice geometric fact that we'll have about them. And so the reason for that, why is that true? Well, it's because of these facts that we just showed. A polyhedron is an intersection of half spaces, and each of those is convex. And so we've shown that half spaces are all convex, and then we've shown that the intersection of convex sets is also convex, and we already know that a polyhedron is the intersection of some half spaces, a finite number, but yeah, so we have an intersection of a bunch of convex sets, so then that itself is convex. So there you go, polyhedra are convex. Yeah, and so you can kind of view this in just a slightly different light now. We can see that each of these individual half spaces were created, and each of them individually were convex, and so then this intersection that comes at when you intersect all the good half spaces together for this purple feasible region that we've been looking at over and over again, that is also convex because it's the intersection of a bunch of half spaces that are individually convex. Yeah, and in contrast, this other one that we showed wasn't convex. You know, what's going wrong is, as you can see, for instance, this constraint here corresponding to this line. Well, in principle, if it were going to be a polyhedron, or in other words, I could realize it as the feasible region to some linear program, well then I'd be writing it as a less than or equal to constraint, but that would mean that the points would only lie on all the points would only lie on one side or the other of this line here. And but we see that, you know, there's points of this shape here that are lying on both sides of this line. And if I were just looking at points on one side or the other, I would have something convex, but because I'm taking both, I get something that has this dent here, and then this dent means that I can find a line segment that enters and exits and re-enters the shape, and so it's not contained entirely in the shape because we have this dent, and so it's not convex. So yeah, so something like this could never be the feasible region of a linear program because it's not convex, and polyhedra are convex. So there you go. So that's the important fact we wanted to show. We'll use that in future videos, but that's the main takeaway for this video. Polyhedra are convex. That's it. Thanks for watching.